I'm Bruce Bugby, president of Apogee Instruments, and I'm going to today walk you through the research we did over several years to develop this new chlorophyll meter. We had this idea quite some time ago, but it took a lot of R&D to get this, and the work we did is published and publicly available in this paper here. I've got a copy of it here. We were really pleased that Plant, Cell, and Environment published this paper. It's one of our top journals because there's a lot of detailed physiology in this paper. And there's so much detailed physiology that I want to walk you through some of it in the next few minutes and with referencing the paper. So here's the meter on a leaf. It's an optical meter. You clamp it down based on the transmission of 2 wavelengths of light. It converts this in software to a unit of chlorophyll per unit area. And in this case, it's moles of chlorophyll per meter squared of leaf. No other meter, optical meter in this price range can do that. That's the unique breakthrough of this meter. But it was not trivial to get to that point. So let's walk through some of the graphs in this, and let's look at what we did. So the first thing we did is a massive literature review, and we found that there are over 30 studies on this relationship between transmission of light and chlorophyll concentration. They started back in 1986. There was a meter called the SPAD Minolta 501, and they later in 1992 they came out the Minolta 502. These are old meters. People are starting to establish this relationship. Here's a critical paper right here, Monge and Bugby, 1992. This is one of my graduate students, Oscar Monge, and I. This paper turns out to be one of my top 5 most highly cited papers in this list because we discussed the inherent limitations of doing this back in 1992. Then about 10 years later, the papers start to show up with an OptiSciences meter, the CCM 200, and getting this, what we call the optical absolute relationship. In other words, the relationship between what this meter can read and the true amount of chlorophyll in the leaf. We know this relationship is nonlinear, which is one of the big problems. But the first thing we looked at was, all right, how do these studies agree? They're on all different species, so let's take a look at that. Here's curves for the Minolta meter. This unit, by the way, people act like this is a measurement of chlorophyll. SPAD stands for Special Products Analysis Division. It's just the name of the division in Minolta that developed it. It's not a unit of chlorophyll concentration. It's a name of a group of people. You can see it's nonlinear and going up, but look at the scatter in studies. Many studies. Here's our studies. The green line right here is the one we did. Then, when we did this again, using more modern techniques, 20-some years later, modern spectrophotometer, more rigorous extraction techniques, we got this black line, which is close to the average of all of these. Now, some people have studied the OptiSciences meter and chlorophyll, and that's also nonlinear, curves the other direction. We did both of these in this paper, in this relationship, but so far, this is literature review, except for our study. All it does is show these papers don't agree. Well, why don't they agree? Well, part of it is because they're different species. Different species have chlorophyll arranged in different packets in different ways, so the light transmits differently. So you really need a line for each species. But look at this. Several papers studied the same species, wheat. They got different curves. For wheat, and one of these is our paper. We went back and looked at these studies, and not one of them used the exact right combination of techniques to accurately convert an optical measurement to an absolute measurement. This is always the absolute measurement here, chlorophyll, which is always what we want to know. This unit down here is what the meter gives us. You have to get several things right to do this. You have to have just the right solvent extraction, you have to have the right equation, and you have to have the right spectrophotometer. All three of those things have to match, and when we looked at the literature, it was very rare for these older papers to do everything correct to get the exact right chlorophyll, including our own paper from 1992. We realized we didn't use the exact right techniques. So when we did it again, this study means this Plant Cell and Environment paper right here, we got this curve. And fortunately, the reviewers agreed, yes, these are all the right techniques. That's the gold standard curve. It replaces all these previous curves, which were similar but not exactly right. Let me make a point here about the problem with older meters. If you clamp on a leaf and you get a reading of 20, you're on this point in the curve, and you have about 100 units of chlorophyll, micromoles of chlorophyll per meter squared. Now you do another leaf, and you get a reading of 40. You conclude, the chlorophyll has doubled because the number is twice as high. Look what happens. We go up here and across. The chlorophyll went up fourfold between 100 and 400, and our meter only doubled. There's the problem. We have a lot of bad data in the literature where people are over-reliant on these SPAD units, and when they should be reliant on the actual chlorophyll and things. And that's a pretty dramatic example of the problem and the misinterpretation of data. So our goal in all of this was to develop a meter where we could convert in the software of the meter to actual chlorophyll units in the meter, not a relative index of chlorophyll, but actual chlorophyll. So how do we do that? Let's take a look. This is a video shot in the laboratory of making an optical measurement with the meter and then very carefully marking where that measurement was. Now underneath this is the reading of the amount of chlorophyll to write down. Now, in order to get the gold standard, you have to take that disc out from the exact same spot on the leaf that the measurement was made. This is done with a cork borer. We put it into a little vial of dimethyl sulfoxide. There's different extraction solvents, but this is the one of choice, and mix it up. So you look in here, you can see this tiny little leaf disc floating in this extraction solvent. The chlorophyll doesn't come out right away, and to speed it up, we put it at 65 degrees Celsius. So here's walking over to a drying oven, putting it in the drying oven with that extraction solvent, and now we wait. And it typically takes about 3 hours until all the chlorophyll is gone from the leaf in solution, still 65 degrees. There's the vial 3 hours later, and now the disc is white and all the chlorophyll's in solution. So step one is extract the chlorophyll. This is one measurement on one leaf. Now, the next step is to bring it into the laboratory and measure it, transfer it into a cuvette, measure it in our spectrophotometer, which scans the appropriate wavelengths and then reads them out on a computer. And we'll zoom in here for you in just a minute on these values, which show the absorbance of those two wavelengths with those two numbers in the correct equation now that matches the instrument and the dimethyl sulfoxide. We can calculate both chlorophyll A and B, and we add the two values together and we have chlorophyll. So as long as your laboratory procedures are correct, This is how you get the gold standard of chlorophyll, but it's obviously a lot of work compared to getting a single digital number. So one of our concerns was that you can't ever have a single curve across a wide range of environments to do this, because the arrangement of chlorophyll molecules will change with environment. We tested that in many ways. We grew plants in many different environments, and our data pretty clearly indicate environment has a minimal effect on the arrangement of chlorophyll, chloroplasts in a leaf. One of the tests of that was to compare our data for paper birch. This is a widely distributed species. This was studied by Richardson, who is at Yale, in 2002. He did everything right in his extractions. We also measured paper birch. Half a continent away, 30 years later, same species. There's a correction in the equation. When we plotted this against Richardson's data, we get virtually the same line. That helped convince us that this procedure is robust across time and space and species. Once we get a curve for a species, that is the curve for that species. And that allowed us to take the curves we developed and put them into the software of this meter. So what do those curves look like? Here's the index from the meter and the chlorophyll here, and you can see all these nonlinear curves. Some species are similar. Wheat, rice, and barley are similar. Some of them are just graphed on the same curve. Pepper and soybean have a remarkably high amount of chlorophyll in the leaves. Scale change was double these other curves. So this is a graphical representation of the curves for all of these. And this is a summary of the species and the numerical equation to linearize the data, and then the R-squared values for these. These are pretty hard to see. You can study the paper and get them exactly, but these are mostly in the 0.9s. There's a 0.97. There's high correlation, coefficients of determination for the fit with these species, which allows us to convert an optical reading to the absolute reading. This is all published in the paper. Here's all of the curves for all the species with the index, and then for species that we don't yet have a curve for, here's a generic curve, and that's the equation to convert the reading to absolute chlorophyll content over here. Lots of species, lots of lines. Only a few species have very dark, very high amounts of chlorophyll. Most of the species are down in here. Along the way, we were able to develop two very accurate curves for converting among optical units from different meters. These special products analysis division units can now be converted to chlorophyll content index, which is what OptiSciences uses, and vice versa. If you know the CCI, you can convert that to SPAD units with these equations, which are pre-programmed into this apogee meter, so you can have this meter read out in any of the units of the previous meters, in addition to the true chlorophyll units. These are very high correlations, 0.98 and 0.99 for these conversion equations. You would think you could do this mathematically, but Minolta has a confidential equation in their meter, and it's not known what the coefficients are, so we have to do it empirically. Now, if you liked logarithms in high school and manipulating logarithms, you'll be interested in this little section of this paper, which is a series of 5 equations that takes us through the percent transmission all the way down to chlorophyll. This is the mathematical relationships that are going on because there's two wavelengths coming through the leaf. And we ratio these wavelengths. The reason this needs logarithms is the transmission of light is nonlinear. When you double the pigment, you do not double you do not cut the transmission in half, and you change the absorbance. So I'm not going to go through the details right now, but this is a ratio of two transmissions, e raised to a power. There's two wavelengths here. This is critical. This NIR wavelength, which is at about 930 nanometers, measures cellulose. I don't have to write it out because it's right here. Measures just the cell wall. This red wavelength, which is at 653 nanometers, measures both chlorophyll and cell wall together. There is no single wavelength that only gives us chlorophyll. We have to ratio two wavelengths. So now you can see how by subtraction we can get to chlorophyll, but we have to deal with this nonlinear effect. So we have e raised to these powers. This ranges to e chlorophyll plus cell wall minus cell wall. Take the log of both sides, solve that for the logarithm. We get chlorophyll plus cell wall minus cell wall equals chlorophyll. And mathematically, this is what these meters read. SPAD should theoretically equal chlorophyll, and the log of the CCI should chlorophyll. Now, this is all done in software in the meters. You don't need to know this. It's just a fun math exercise if you like following the math. It took us a while to work through this in the lab to get this, but it's very satisfying once we showed it theoretically what's going on. These are the species in the apogee meter for which we have equations. We're working on additional equations for this. There's generic equations in here. Most of the major annual crop species are in here. There's a number of deciduous species also in this. So that's a summary of what we had to do to get to this point. To make this meter read out in moles. This doesn't say anything right here, but this is moles of chlorophyll per meter squared, which is what you get with a spectrophotometer, and it's now what you get with this non-destructive optical meter. For details, I refer you to our paper in Plant, Cell, and Environment. And contact Apogee for a copy of the paper, and it's also available on the internet. Thanks for listening. We look forward to another visit.